Hello everyone, today let's take a look at QP number 77, another question about covariance, correlation, all that stuff. So suppose you roll a standard fair six-sided die n times. Let x be the random variable representing the number of times you roll a 1, and y will be the random variable representing the number of times you roll a 5. So what is the correlation between these two random variables? So x is the number of times that we've rolled a 1, and y is the number of times that we roll a 5. We want to find the correlation between x and y. Again, at this point, we know what the correlation between x and y is defined as, right? It's just going to be the covariance between them. So the covariance between x and y divided by basically each of their standard deviations. So the standard deviation of x and the standard deviation of y. And now when you look at this question, you notice that we are basically both for x and y counting the number of times that we do something that is exactly the same. So what does that mean? Well, we're going to be able to simplify this using indicators. First of all, let's look at the random variable x, right? If I have my n different dice rolls right here, let's say ... all the way up to n, well then for each of these, I'm going to define basically I sub j, which is going to be equal to 1 if that number is a 1, and it's going to be equal to 0 if it's not. And then I'm going to define the same indicator for my second roll, right? It's going to be equal to 1 if that roll is a 1 and 0 if it's not. And then for every single one of my n different rolls. And now x, which just represents the number of times that we rolled a 1 among all n flips, can just be expressed basically as the sum from I equals 1, actually j equals 1 to n of basically I sub j. Now for y, I can basically just do the exact same thing. For y, I'm going to say for my first roll, I'm going to define another indicator, I sub k, let's say this time that's equal to 1 if the roll is a 5 and it's equal to 0 if it's not. And again, I'm going to define the same indicator for all of these basically n flips, and then we can express y as just the sum from basically k equals 1 to n of I sub k, right? For the same reasons as we can up here. So what was the point of expressing these as indicators? Because now we can use linearity of expectation, linearity of variance, and it's going to simplify this problem greatly. So first of all, for the standard deviation of x, first we need to compute the variance of x, right? So what is the variance of x? Well, it's just going to be the variance of this sum of indicators right here. So let's look at that first. So we've talked about what this value right here is a lot, right? In QP41 and QP145, we know that this is just going to be equal to basically, well, the sum of the variances from j equals 1 to n, so the sum of the variances of I sub j, and then we're going to have to add on 2 times all of the pairwise covariances. And then for that term right there, we're just summing up over all of the pairwise covariances, right? All of the ordered pairs, because then we're multiplying by 2. Again, we talked about this a lot more in QP41 and QP145. However, what we also talked about in QP41, if we're taking the variance of a sum of indicators and all of these indicators are independent, well then we're not going to need to worry about this covariance term because every single one of these is going to be 0. But now what do all of these indicators represent? Well, they're all independent dice rolls, right? So all of these indicators right here are independent. So therefore all of their covariances are going to be 0, which we talked about much more in QP41, right? But this is just going to be equal to the sum of the variances. So again, linearity of variance only works. We can express this term as this one if all of the indicators are independent. If not, we're going to have to add on 2 times the sum of the covariance terms, right, like we had before. Now, what is the variance of an indicator? Again, we've done this a bunch. We derived in QP91 what the variance of an indicator is. It's just going to be p times 1 minus p, where p is the probability that it is equal to 1. So in our case, first of all, we're looking at I sub j, which is equal to 1 if a dice roll is a 1 and 0 if not. So the probability that a random dice roll is a 1 is obviously just going to be 1/6. So we have 1/6 here times 5/6, right? That's 1 minus 1/6. So then this is going to multiply out to 5 on 36. And then we're summing up that constant value of 5 on 36. We're summing that up n different times, right? So we just have n times 5 on 36, and that's going to be the variance of x, which means the standard deviation of x is just going to be the square root of that. So the variance of x is 5 on 36 times n, and now the variance of y we can compute in much the exact same way, right? Because y, we're just summing up these indicators, which again represent these independent dice rolls right here. The only difference is that an indicator is equal to 1 if the roll is a 5, where before it was a 1. But we're still modeling independent dice rolls, so we can use linearity of variance. We can just sum from k equals 1 to n of just I sub k, right? And that's going to be the variance of I sub k in the inside here. So again, because all these dice rolls are independent, we don't have this covariance extra term, right? So we can just have this. Now the variance of this indicator is just going to be p times 1 minus p. So what's the probability on a random roll that I get a 5? Well, again, it's going to be 1/6. So p times 1 minus p is just going to be this number here again. So the variance of each of my indicators in this case is also going to be 5 on 36, and I'm summing them up n times. So the variance of y is just going to be the same as the variance of x. It's going to be n times 5 divided by 36 as well. Okay, so now new page, we just showed that the variance of x and the variance of y are both both going to be n times 5 on 36. So the standard deviation of both of them, right, the standard deviation of x is just going to be the square root of that. So we're just going to have the square root of n times 5 on 36, and the standard deviation for y is going to be the exact same thing, right? So when we multiply these two things together on the bottom of our correlation equation, right, these square roots are just going to go away. If we multiply the square root of the exact same thing by itself, right, it's just going to be on the bottom here. This term is just going to be n times 5 on 36. Now for my top term, the covariance of x with y, that's going to be a little bit more challenging. It's basically just going to be, well, we know that we can express this as the expected value of x times y minus the expected value of x times the expected value of y. That's from QP 147. Now again, x was the sum of these indicators right here, so the expected value of x should be very easy to calculate. The expected value of an indicator is just the probability that it's equal to 1. So what's the probability that we get a roll of 1 on any given dice roll? Well, it's just going to be equal to 1/6. So we're just summing up 1/6 here n different times, so it's just going to be n divided by 6. N divided by 6 is going to be the expected value of x, right? When we're taking the expected value of all of these indicators inside, that's linearity of expectation, right? Now the expected value of y, again by linearity of expectation, is just going to be the sum from k equals 1 to n. Remember, we can express y as the sum of these indicators, so we can use linearity of expectation to express the expected value as the sum of the expected value of all of these indicators. The expected value of an indicator is just equal to the probability that it's equal to 1. So in our case, for y, we had the probability that the indicator was equal to 1 if that dice roll was a 5, right? So the probability I get a 5 on a random dice roll is going to be 1/6. We sum that up n times, we again get n on 6. Both of these make a lot of sense because if we roll a dice n times, then obviously we're going to get a 1 n out of 6 of those times, or we would expect to get n out of 6, and then we're going to get a 5 n out of 6. We're going to get 1, 2, 3, 4, 5, 6, each n out of 6 times. So that takes care of those two terms right here. This is just going to be n squared divided by 36 when we multiply n on 6 times n on 6. Now probably the hardest part, the last thing we need to do is the expected value of x times y. So let's look at that down here. So the expected value of x times y is just the expected value of this sum of indicators times this sum of indicators, the same ones that we've been using for x and y. I guess it didn't matter before, but I should have been using a different indicator name for y than I was using for x. So let's have basically this one be j and this one be I over here. And then we got to change this index as well for it to make sense. So we're summing up from I equals 1 of I sub I instead. So j sub k is equal to 1 if that roll is a 5, right, representing y. And basically I sub I is going to be equal to 1 if the roll is a 1, so representing x, right? So I'm just summing up here over every single pair of I and j, right? We can more cleanly express this basically as this double sum where we bring all the double sums outside, right? So I equals 1 to n, and then let's have k equals 1 to n, and then we're just going to have I sub I times j sub k. That's because when we multiply these right here, they don't really depend on each other. Their iterators don't depend on each other, so we can just write it like this. And now we're taking the expected value of this term inside here and linearity of expectation, right? We're just taking a bunch of sums here. We can bring this expectation inside. So we're just summing up over every possible combo of basically I sub I and j sub k. So if I is equal to k, right? For instance, if I starts at 1 and then we're doing k equals 1 right here, right? We're talking about the same dice roll, right? We're talking about dice roll number 1. And the expected value of the multiplication of two indicators is just the probability that they're both equal to 1. So what's the probability that this dice roll right here is both a 1 and a 5? Well, obviously it's going to be 0 because it can only be 1 at a time. So the expected value when I is equal to k is going to be 0. Now in the other case, if I does not equal k, so for instance, maybe I sub I, maybe we're talking about I sub 1 here and we're talking about j sub 3. Then the expected value of their multiplication, again, is the probability that they're both equal to 1. We've talked about that in previous videos, right? So basically the probability that this one is going to be a 1 times the probability that this one is going to be a 5 because this one is j and this one is I. Now all these dice rolls are independent, right? So they have 1/6 probability each. So when we multiply them, basically the probability that they're both equal to 1 is just going to be 1/6 times 1/6, which is just equal to 1 on 36. And the same is true for the expected value of any two cards that are not equal to each other, right? So these two and then these two and then every single pair, right? Now how many of these different pairs can we sum up over, right? How many are we summing up over right here? Because now we know that there's just a constant here of 1 on 36 when they're different. So how many different pairs do we have? Well, it's just going to be n choose 2. I have n rolls of my dice and I want two different ones, right? So n choose 2. And then I'm going to have, for instance, I might have chosen j sub 3 and I sub 1. But also in this same sum, I'm also going to be counting basically when they're switched. So j sub 1 and I sub 3, and that's also going to have a probability of 1 on 36, right? So we need to basically double count all of our ordered pairs. So we multiply by 2. So this number right here is the total number of times that we are summing up this 1 out of 36, right? It's 1 out of 36 again because these are two independent dice rolls. So the expected value of their multiplication is the probability that they're both equal to 1, which is going to be 1 6 times 1 6, which is 1 on 36. So the expected value of x times y is just going to be 2 times n choose 2 times 1 on 36, right? N choose 2 is just equal to n times n minus 1 divided by 2. And then these 2's are going to cancel right here. So we're just going to have a final answer for the expected value of x times y of n times n minus 1 on 36. Okay, so now finally we have everything we need to basically solve for the correlation, right? That was our final term, and it's going to be, well, what was it? It was n times n minus 1 divided by 36. Now all that's left to do is just plug in all these values into one formula and get our correlation. So we're taking this term and subtracting this one. That's going to be pretty simple. We can put these already over a common denominator, right? This is just going to be this over this, and then this right here is just n squared minus n. So we're taking an n squared, we're subtracting an n squared. These are going to cancel, so we're just going to have negative n on 36, right? That's the covariance between x and y. So that's the term on top of our correlation, and then remember we got n times 5 on 36 for basically the multiplication of our standard deviation. So n times 5 on 36, and then on the top we have negative n on 36. So we can do this pretty easily. This is just going to be equal to negative n on 36, and then we can invert the bottom. So it's just going to be times 36 on basically n times 5. The 36's are going to cancel, the n's are going to cancel, and we're going to be left with just negative 1 on 5. So that is the correlation between x and y. So that's the final answer. Now, does that make sense? Well, yes, it does, because we would expect a little bit of a negative correlation, because for instance, if I get a bunch of 1s, right, if the number of 1s that I get through my n flips is higher, well then the number of 5s that I get should be a little bit lower, right? So they have a slight inverse relationship. So similarly, as the number of 5s that I get increases, so basically the value of y increases through my n flips, I'm going to expect to get less and less 1s, right? Because there's going to be less of them to give out if there's more 5s, right? So that's why we have this slight negative correlation between the two.